So, what's the occasion that you need to meet me in this morning, huh?
I need to tell you that we have problem here.
What problem?
Let me explain to you about the problem. Before jumping into the main problem, let me explain first about linear algebra. It's a system of equations that can be represented as a product of matrices or as an augmented matrix. There are also special types of square matrices with unique properties. Therefore, there are two methods here. First, direct method, which the aim is to solve the problem with an exact solution. We can use it on finite linear equations since they are good for dense systems of small to moderate size. It can be applied with Cramer's rule, Gauss elimination, and Gauss-Jordan. Next, we have indirect method, which is also known as iterative method that requires only lesser computational effort. It is very much acceptable if the iterative methods give approximate solution within a convergence criterion. Also, it is more preferred when the matrix is very big and sparse. Indirect method is used for very large matrices since they reduce the round-off problems. That error can be considered to accrue only during the last iterations, where it can be applied with Gauss-Seidel and Jacobi method. In this problem, we are going to use Gauss-Jordan. Gauss-Jordan is an algorithm that can be used to find the inverse of any invertible matrix. Now we have reached to our main problem. The members of the truss shown in the accompanying figure have a cross-sectional area of 20 cm square and are made of aluminum alloy with elasticity around 70 gigapascal. We need to determine the deflection of each joint, the stress in each member, and the reaction forces. We have to verify our results. So, Vincenzo Casano, how do we solve this? It's easy. First, we define the parameters. Here we create a table of element node I and node J. What is node? Node is node which connects each element. Let's take an example from Truss. There are element 1 and element 2. Between them, node I is located on element 1 and node J is located in element 2. So technically, it's the dot which connects each point. We also have the area, which is 20 centimeters square or 2 times 10 to the power of 3 in meter square. Then there's the elasticity around 70 gigapascal, and there's a force which gives pressure on point 4 around 10,000 newton and a fixed support at element 1 and 3. In order to easily solve this problem, we're going to use open modelica. First step is partitioning the problem into nodes and elements, just like we have done before. Next, we create a parameter for a member and node load. The parameter for a member consists of element node I, node J, theta, area, modulus, and length. Meanwhile, for a parameter of node load, it consists of node fx, fy, ux, and uy, where we put 1 if it's fixed. Second step, assuming a solution that approximates the behavior of an element by using this formula. K is equal to area multiplied by elasticity, then divided by length. Third step, developing equation for elements. The equation will be used for next step. Here we need to convert the stiffness into global format. We're going to find the corresponding global matrix coordinate and transfer the value into its position in global format. Fourth step, assembling the elements into final form. Fifth step, we are going to apply the boundary condition and loads. Sixth step, it's time to solve the system of algebraic equations simultaneously. We already have the local variables to help us dealing with the Gauss-Jordan algorithm. Next, the operation will be solved with the help of open modelica. Don't forget about the floating point errors that we have to deal with so it will perform better. We're now stepping into the post-processing phase. First, finding the reaction forces. Then we can continue by finding internal forces and normal stress. We are set. Here we already have the result. First, we get a graph of our displacement. Next, we have the result of our reaction forces. Here we know that there is force in node 1, 3, 5, and 6. Plus, it's the result of internal forces and normal stress. And here you can see the value of each point. It's done. The problem now has been solved.
So, how is it? Everything is clear, right?
Yes, sir. Now the problem is finally solved. Thanks to you. I just need to inform this to the others so they'll fix as what you've just told me before.
Sure, no problemo.